integrals are perhaps the most important part of calculus. And so because of that, I'm going to start all the way at the beginning to make sure you really know what an integral is and where it comes from and why we invented it. Imagine you had to find the area under a graph. And it's pretty simple for a linear graph like this. Let's say you want to find the area from 0 to, here's A, and then here's f of A. Well, for this, if you want to find this area, you can just do 1/2 base times height, which in this case is 1/2 A times f of A, right? So if you want to find the area under something like this, that's pretty simple. But now what if you have to find the area under this? Right, there's no elementary shape that we can just put in here and find the area of and call it a day. So what do? Well, we know we can't find the exact area with elementary shapes, but maybe we could approximate it. So an easy shape to find the area of is a rectangle. So I'm going to go ahead and fill the area under this curve with the rectangles. I'm going to do it two ways. Okay, now I've filled it such that these rectangles are supposed to be equally spaced apart, but every time I've gone and drawn up a line, I've gone until it reached the graph, and then I went left. So you see how I did here? I went up to the graph, went left to meet the x-coordinate here, and then came down to make the rectangle. And so this is called a left Riemann sum, named after mathematician Bernhard Riemann. Riemann is known for his method of approximating areas using rectangles. And so this, when you go from here, the axis, to the function, and then you go left, this is called a left Riemann sum. And now look how I've drawn the rectangles under the same graph. But this time I've gone from the axis to the curve and then gone right the separation distance and then met it with another vertical line from the next rectangle. So starting from the axis, going up and going to the right is called a right Riemann sum. And so these left and right Riemann sums are used to commonly approximate areas under curves. But if you'll notice, there's some that we missed here, 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 like this. All this we missed. And there's some that we over approximated. Like here, this is sticking above the graph, and we missed this, we missed this, and we missed this. So how can we make this better? Right, well, first let's try to, let's try to keep the rectangles all inside the graph, and let's see what happens. Now, more or less, all the rectangles are inside the curve. But we're still underestimating because we're missing some of this. We're still missing a lot of the curve, right? So how can we make this better? Well, right now we're summing areas of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 rectangles. What if we increased it to 26? Then what would it look like? Okay, now we're at 26 rectangles, but we're still missing a bit of the area under the curve. So what can we do? We'll go to 52. Well, why stop at 52? Why not go to 104 or 208? Or what about infinity? What if we split the area under the curve into an infinite number of rectangles and added them? Surely that would get us a really good approximation of the area under the curve, right? Yes, it would. And now I'm going to mathematically write out in equations what we just did on the board. So first off, let's think about what a rectangle is, right? It's a height times a width. So if we had a graph like this and we have a rectangle here, we can say that the width is x and the height is f of x. And how about we change this x to delta x, right? This change in x, the width of the rectangle. So how would we write the area of a rectangle? Well, it's length times width. So it's f of x times delta x, right? And in the clip where we summed 13 rectangles, we added from, so we had 13 rectangles, right? So that means we had to have 13 y values that we made rectangles out of and summed to get an approximation with 13 rectangles, which, by the way, because they were all under the curve, they were less than the real area. Oh, and by the way, this is called a sigma sign. This stands for adding. So what this means is you're adding the first height times delta x, so the first rectangle, plus the second height times delta x, the second rectangle, and so forth until you add the 13th height times delta x, or the 13th rectangle. So this is just all this condensed into sigma sign. And going from 1 to 13 signifies that we're starting at the first rectangle and adding to the 13th rectangle. What if we go to 26, right? As we did in the next clip. Well, then we'd get the area of 26 rectangles, which is still less than the real area because they were all under the graph. But do you remember how we had less blank space with 26 rectangles than 13? So the area of 13 rectangles is less than the area of 26 rectangles, but that's still less than the real area. Notice how by doubling the number of rectangles, our estimation got better, right? It got closer to the real area. So what if we did, so if we kept going in times 2s, we'd have area of 52 rectangles is greater than this. Area of 104 would be greater than that, and so on and so forth until we got to the area of infinite rectangles. But the area of infinite rectangles poses an interesting question, because how wide is a rectangle for you to fit infinite rectangles inside of a given space? Well, the answer to that is you can't really numerically signify it, and we have to show it as a differential, or dx. In this case, dx is an infinitesimally, that means very, very small, an infinitesimally small value of x. What if we make dx the width of the rectangle, like we said? So, actually, before we do that, Let's talk about how we would turn this into an infinite sum. The process that I just took you through, where we went from 13 to 26, I didn't do 52, but obviously if we kept going, we would have gone and gone and gone and gone to infinity, right? So we can represent that as a limit of summing n rectangles, and you take this to infinity. So this becomes a of n rectangles, and as the n goes closer and closer and closer to infinity, it gets closer and closer and closer to the real area. But how do we actually get the real area? Well, if we want the real area, we have to change how we're adding. Right now, using the summation sign, we're adding discrete areas. Like we're adding one rectangle, two rectangles, all the way until we add n rectangles. But we're never going to add an infinite number of rectangles because that would just take way too long. So we have to find a way to make this faster. And remember how I told you this is a discrete sum? What if we had a continuous sum? Namely, the integral. This is where the integral comes in. So the integral sign, like this. Notice how we still have f of x, but instead of the delta x, we have dx, the infinitesimally small change in x. What this means is we're adding an infinite number of infinitesimally thick rectangles. If we did that this way, we would never, arrive at an answer by doing discrete addition. A way you can think about the integral sign is kind of like a hybrid of the sum and the limit. So, you know how if you were adding discrete rectangles under this curve, you'd be going like, okay, 1, 2, 3, 4, 5, 6, 7, 8. But with the integral, you just continuously sweep out the area under the curve. So in theory, we are still adding an infinite number of rectangles, but we're taking the sum, we're making it continuous with the limit, and that gives us the integral sign, which now, because it's continuous, it doesn't miss anything, right? It always gets 100% of the area under the curve. So this is the way you get the real area, and that's what integrals are used for.